after talking about the angular kinematics, all the physics quantities, you can see that you can feel that it's actually pretty much the same as the linear kinematics, except that everything now is at angle. So the unit will be radian. Okay. So since they share such a similar structure, so we can borrow all the physics, like all the relationship that we learn in linear kinematics and move it to angular one. So for example, angular displacement is just a change in angle. Our usual VT relationship, okay, V so omega is angular velocity. Our usual VT relationship in the angular version is also the similar. V final equals to V initial plus AT. And this is our usual XT relationship. Change in the position is VIT plus 1/2 AT squared. And this is our usual VX relationship. V final square equals to VI squared plus 2A delta X. Okay. So because like the meaning of them is they're sort of constructed in a similar way. So all the relationship which is applicable in linear, you can find like a one-on-one, like one-to-one correspondence in angular as well. Okay, so this is the relationship between all the physics quantities in angular motion. Let's try out an example. So here I list all the relationship in case you don't remember that. Okay. You can ignore this one for now. We usually use this 3. Okay. So say there's a DVD and there's a line, PQ, and as the disk begins to turn at the constant rate, and then at time t equals to, at the point per second, what's the angle between PQ and positive x-axis? So this guy is going to turn. So maybe after 0.4 seconds, it's gonna be here. So my question is, what's this angle? Okay, so since I wanna find the angle displacement, so I will start from this equation, the xt relationship. This equals to the initial velocity plus this. Okay, the disk begins to turn, so which means the initial angular velocity is 0. Okay. The acceleration is 5, angular acceleration is 5. The time is 0.4. So after figuring out this math, I get 0.4 rad. So this angle, this angular displacement is 0.4. The answer is A. All right, so it's pretty much the same as linear kinematics, but now we're kind of dropping a lot of new physics quantities, so it takes some time to make that conversion in your head. So another connection that I want to make here is connect the angular motions to the linear motion. Because remember that our initial motivation to study angular motion is because it's easier than the linear motion, the tangential linear motion. So how do I connect it? Like once we figure out the angular, like for example, once I figure out, say when my ball goes from here to here, the angle here is theta. Okay, so say this is 90 degrees or pi over 2. Then how do I know what's the linear displacement? Like what's this linear displacement in tangential direction? Okay, what is this? Okay, so this is, so I'm gonna call this delta S. This is that's just a common notation we used in tangential displacement. So I'm gonna call this arc delta S and call this theta. delta theta. So if you can recall, like in high school, you probably learned that the delta S, the arc, this arc is nothing but the angle times the radius. So the arc is the angle times radius. All right. Okay. So we will start from here. And now you can take this equation divided by delta t. And you can see delta S over delta t is the velocity in tangential direction. Delta theta over delta t is the angular velocity. So from this equation divided by delta t, we get another relationship that can connect angular velocity to our tangential velocity. Okay. And similarly, I can divide it by delta t again and get this relationship. So in summary, if we observe this, the relationship between angular motion and the translational tangential motion, you can see that they have a one-on-one like a correspondence where linear is nothing but the angular times the radius. So same for all of them. If you want to find the linear velocity, you just take angular velocity and multiply it by r. If you want to find the tangential acceleration, linear tangential acceleration, you just find the angular acceleration and multiply it by r. Okay. So you can see they have a pretty close relationship like between them. All right, so now we talk about two sets of relationship. One is a relationship between angular motion. One is a relationship between angular and the linear motion. Okay. Now I'm gonna talk another set of a relationship. It's a relevant. It's related to some other physics quantities. So these are two physics quantities that you will see a lot when we talk about circles. One is called period. One is called frequency. Period is the time it takes to do a full rotation. And we call it T. Frequency is how many full rotations can you do per second. That's what we call frequency. So period has a unit of second because it's how much time it takes. Frequency has the unit of 1/2, or we say hertz. Hertz, and it just means how many rotations you can do in 1 second. So this period is also a physics quantity related to omega, because you can think about what's the meaning of angular velocity. Angular velocity is the change in the displacement over the change in time. If the displacement is 2 pi, then the time it takes to rotate 2 pi will be t. So t is also 2 pi over omega if you swap these two. Okay. So period is also related to omega. And frequency is also related to t, to the period. Because, frequency is just like 1/t, how many full rotation you can do in 1 unit. This is rotation over unit time. Okay. If you inverse that, then that's the meaning of period. Okay. So I hope this makes sense to you. And so you can see T, omega, and the frequency. They are they are pretty much the same thing. They just they are all the physics quantities that are used to categorize the time of the angular motion. So let's do a review. We have introduced a lot of physics quantities in one lecture. So today we introduce a new physics quantities in for the angular motion. So we talk about angle, angular velocity, angular acceleration. We also talk about period and frequency, which is closely related to angular velocity. Okay. And then we also talk about the relationship between them and talk about the relationship between the angular kinematics to linear kinematics. And it's pretty much, angular times the radius will become the linear. All right, so that's all about the angular kinematics.